number 123 is a little tricky one. So there are a bunch of salts, and we're trying to figure out which one will produce a basic solution. Now, if this was a multiple choice question, you could try to eliminate some right off the bat. So like sodium chloride, if you pretend that that's a double displacement reaction, you'd get sodium hydroxide plus HCl. Well, strong acid, strong base, obviously that's going to give you a pH of 7. So sodium chloride is not a possible answer. But the other ones, they all could possibly give you a basic solution. So let's just write a generalized equation. We don't know what the, they're all sodium. Let's back it up, make it a little bit more obvious. So all of the salts are sodium. A stands for just the rest of the molecule. So you know that it's going to give you that. So whichever the salt is, you're going to have A minus. So A minus plus water is going to yield this. Okay? The concentration of A minus is 0.1 moles over 1 liter. Okay? That gives me a molarity of 0.100 molar. We haven't done this too much, but when you do an ice table, it must be in molarity. Okay? In chapter 15, it'll become more clear why the ice table must be in molarity. But every problem we've done so far, they've given us the molarity to begin with. So we've got 0.10 molar of this, 0 of this, 0 of this, shift right, 0.100 molar plus x plus x, okay? Oops, sorry, minus x there. So then when we do our Kb expression, our Kb expression is going to be concentration of HA over OH over concentration of A minus. Well, we know the concentration of A minus. We know it's 0.100 molar minus x. However, the x is going to be too small, so that means the concentration of A minus is just going to be 0.100 molar. The concentration of OH minus we can figure out from the pH. They told us the pH was 8.07, which means that the POH must then be 5.93. So then we can find the concentration of OH based off of the negative log. So the concentration of OH is going to be 1.2 times 10 to the negative 6 molar. Which will then also be the concentration of the HA because they both have to be equal. Okay, so now we have everything we need to know in order to plug it in to find the Kb. So then my Kb will be 1.26 times 1.26 over 0.100 molar, and that will give me a Kb of 1.4 times 10 to the negative 11th. Okay? So I know the Kb is 1.4 times 10 to the negative 11th. So that's for A minus. Well, then the Ka times Kb is equal to Kw. I can find then the Ka by plugging that in and find the Ka of the conjugate acid. So the Ka of the conjugate acid is 7.1 times 10 to the negative 4th. Okay? So I can take this and compare it to a table of acids in the book, and I could find the closest one is hydrogen fluoride. Hydrogen fluoride has a Ka of, let me just check it here real quick. (7.2 times 10 to the negative fourth). So it's very close, okay? So all of these salts that they gave us as possibilities, whoops, here are all the salts they gave us. Those are all the bases. The conjugate acids are this. So we found the Ka to be 7.1 times 10 to the negative fourth, which means that's the closest to that one. And that's the answer to 123. All right, one to go. Number 129. All right. Are the solutions of the following salts acidic, basic, or neutral? For those that are not neutral, write the balance of chemical reactions. Wow. Maybe I shouldn't have given this one to you. Sodium nitrate. Gives you sodium hydroxide plus HNO3. That's strong base. I'm sorry, strong acid, strong base, neutral. B. Sodium nitrite. So if we do this one, we're going to get sodium hydroxide plus NaO2. This is, sorry, that's not, there we go, HNO2. This is weak acid, strong base, so this is basic. C, oh boy. You've got C5H5NH and then ClO4. It would have been nicer if they would have showed you that to help you identify where it breaks apart. So that's going to give us C5H5NH2 plus HClO4. That's a strong acid, weak base, acidic. D, NH4, NO2 plus water. It's going to give us sodium hydroxide plus HNO2, strong base, weak acid. This one's going to be basic. I'm just going to check on that one real quick. See. Let's see here. actually, this one is indeterminate without being given Kas or Kbs. So remember when I said that this is a quick way to do it, but the actual thing that's going on is the ammonium will break apart and give you this and give you this. This reacts with water and would give you NH3 plus H3O plus, which would be an acid. This one would react with water and give you this, which is a base. So the question is, who's stronger? Well, you can't tell because this is a weak acid, this is a weak base. So you cannot tell just by looking at the problem whether it'll be acidic or basic. What you need to do is compare the Ka and the Kb of each and see who is bigger. If the Ka is bigger than the Kb, it'll be acidic. If the Kb is bigger than the Ka, then it'll be, I think I just wrote the same thing. If the Ka is greater than the Kb, it'll be acidic. If the Ka is less than the Kb, then it'll be basic. So there's not enough information to tell for letter C. Letter D is what we just did. So let's move on to letter E. This would be potassium hydroxide plus HOCl, weak acid, strong base. This one's basic. F, ammonium, OCl. This is going to be like the last one. You're going to generate these two, this salt is going to break apart and give you this. NH4 is a weak acid, so when it adds to water, it's going to make H3O plus NH3. This is an acid. The OCl minus, that's going to react with water, and that's going to generate HOCl plus OH. That's a base. So you cannot tell whether the solution is going to be acidic or basic because here you've got a weak acid, here you've got a weak base. So once again, like in that other problem, if the Ka is greater than the Kb, it'll be acidic. If the Ka is less than the Kb, then it'll be basic. Okay, but there's no way you can tell just by looking at it. So thank you very much. I hope this is helpful.